just a little bit of background. I organize I'm one of the people who organize a similar meetup in Zurich in Switzerland. Yeah, and so that's one of my wishes, was just to see here and see how one of these meetups works in another country. So in case you're in Zurich, you're more than welcome to come to the Zurich Haskell meetup. And by doing a talk at this meetup, I'm also then relieved of my duty to give at least one talk in that's a condition that we have at the Zurich Haskell meetup, that everyone has to give one talk, but they didn't say where. So it's cool that's being recorded. There's proof. Okay, cool. So I asked James, what should I talk about? I have a number of topics, and he said that this may be something good. So I'm going to talk about Hoogle for the hungry masses. So if you like Hoogle, I'm going to show you how this can be done for any other language, any other mainstream language. So this is joint work with my student, my ex-student now, Mehta, who's there, right? And yeah, a little bit about myself. So I'm not from here, so let me just tell you. So I work in a university called the OST, the Eastern Switzerland University of Applied Sciences. Who's been to Switzerland? Oh wow, okay. Who's been to the OST? Some of you. Nice. Okay, not many, but cool. So it's one of the bigger technical universities in Eastern Switzerland. We have computer science and other schools and things like that. But more importantly, for the Haskell community, this is the university that hosts an event called ZuriHack, which is currently the biggest functional programming community event in the world. So last time we had about 420 people. So yeah, I'm happy to do this. It started off small. And so who's been to ZuriHack? Oh wow, nice. Wow, okay, our Rust cameraman has been to ZuriHack. Crazy. No, okay.
14.
Nice. But that time it wasn't here, it was another place though. Yeah, nice. Yeah, okay, cool. If you haven't been to ZuriHack, I welcome you to please join in, right? So here are some of the places, some of the logos that we have. This is our university there, and it so happens that the logo that we chose for this year is a Japanese themed logo. Pure coincidence. So my neighbor is a Japanese designer, so yeah, so feel welcome to join in. Anyway, so now to the topic, right? Who has used Hoogle? Okay, few of you haven't. Hoogle is a type-based search engine. Yeah. So think of this, right? There's something you want. You want a function. A programmer, first thing he does, has someone already implemented this function. Typically, one would like to search using a specification, right? And types are a good form of specification. So yeah, so some of you use Hoogle. Let me just show it to you. For those of you who haven't, let me just show it to you quickly. My web browser. There we are. Let me make this a bit bigger. So here is, can everyone see this?
Yeah.
Yeah? Okay, good. So let's say I want to search for a function. I want to filter a list. I don't know, I have a list and I want to filter everything that's a telephone number or something like that. So I say, oh, well, I know that its type should be, it should take a list. It should take something that tells me if I want this element to be in the list or not. So I say, well, I give it a function, let's say a arrow bool. I'm sorry, I'm using a keyboard I'm not used to. Arrow a list, arrow a list, right? And magically it tells me all the functions that have similar type signatures, exact or similar type signatures, right? So, and I see, voila, there I have my filter functions there, and I know where it is and all that stuff. And this is great, right? Haskell programmers use it a lot, and it's really nice. And I've asked Java programmers, do they have something like this? They said no. And so, and I asked them again a few years later, they said no. And a few years later, they said no again. And so I thought that someone has to do something like this. Someone has to do something like this. Anyway, so let's So I have a collection of these ideas, and I keep them for unexpected students. Yeah, and so I'm there, and so this is how this project actually started, right? So Mark was doing something, some specification of Java stuff, something yeah, quite unrealistic, and we were doing our stuff, and he did a project with me in Haskell some time ago. And this project we were currently doing was not going anywhere. And we were both a bit frustrated and everything, and we were doing some stuff on the computer. And he said, it would be nice if we had something like Hoogle for Java. And then this bell rang in my head. I said, I have this topic on my list actually. And I said that, yeah, if you want, you can actually do this. But he said, but I already have a topic and we're currently working on this thing. And I said, no. You have 2 tries at your master's project. Yeah, you can fail once. So why don't you just fail this, and then we do this as your next master's thesis. And I thought this was like a bluff. This was like a joke. And he called me on this bluff, and I called him on this bluff. And so I failed him. And the next and the next semester we did this. And this ended up being quite a big success. And yeah. So that's how it all started. Yeah. So we want a nice text-based search, right? We want a nice search, and we want to search for our functions, right? So currently, people use Google. I mean, now it's the time of AI, but at that time it wasn't so hepped up. But at the time, we just search on Google, find something on Stack Overflow. But this was very suboptimal, and we know this from as Haskellers, right? And so the idea of a type-based API search is actually quite great, and we've seen that there are some people who use it. The Haskell community already uses it, but it's only available to a select few. How would it be if everyone could use something like this? Yeah? And so that's how this whole thing started. This is not the first time we tried to tackle this problem. In 2016, another student tried this, and we did this for Scala. So he did this for Scala. There was a paper in Splash on this, the Scala API search. And at that time, he did it using classical search techniques, which means Lucene search, so the standard Apache stuff with vectors and all that stuff. And it sort of worked. The Scala community enjoyed it and everything, and okay, that was good. And so we claimed that this was general and all that. And so I told Mark at that time, I said that, hey, try this out. Maybe you can make it general. And he tried it out, and he said that it's working, but it was really a bit too ad hoc. These things are very ad hoc, I find. You have to tweak that, and then you tweak that, and then you tweak that, and it was not a lot of fun. And I kept on telling him at every meeting, have you taken a look at dependent types? And he always looks at me like, what are you talking about, man? And then he said, I'm doing this Lucene search. Do you have a way to make this vector okay? I was like, have you taken a look at dependent types? He's like, what is that? What is wrong with you? And then, so I kept on saying this, and at one point he said, come, let's take a look at this, right? And so we ended up with this thing that I'm going to present to you right now. Yeah, and so what are the cool things in this approach? So just going back, so we tried to use type theory, yeah, to do this sort of search, API-based search, yeah, and in a sort of generic way. Right? By generic we mean this is language agnostic. Yeah, we had to have some sort of baseline of what type of language we're looking at, and we said we want a language like the lambda calculus plus ad hoc polymorphism, parametric polymorphism, and subtype polymorphism. And for those of you who have read Benjamin Pierce's book, we sort of say that subtype polymorphism doesn't play very well. So I was a bit skeptical about all this in the beginning. But I said, hey, it's Mark's master thesis. What have I got to lose? And so we tried it out. And it was quite cool. So what was really good about this approach? So it's targeting mainstream languages, not just Haskell, not just functional languages. Yeah? It's inspired by the Curry-Howard correspondence. A reviewer told me that, hey, you have to call it inspired by, because actually you're not really using dependent. So it's not really using dependent types to execute the stuff. It's just using the proofs to search. Yeah? So we moved from an ad hoc framework to a general general framework, yeah? And we translated through this lens of Curry-Howard, so the mirror of Curry-Howard, we sort of translated a type search problem into a proof search problem. And my hope was that we can use existing provers to search for these things. But that was not as easy as we thought. So I'll come to that later. Yeah. And funny thing was, once we made this general, yeah, it turned out that we didn't just do type search, we didn't just do searching for one function, we actually were able to synthesize programs that matched this type, right? So Mark called me up one day, he said that, hey, this algorithm is sort of not giving me just one function, it's giving me like combinations of functions that match this type. And I was like, cool, that means it's working. Yeah, so those are some nice things that we weren't expecting. Anyway. Cool. So let's go into it. How does this work? First, a little architectural overview. What really happens? How do we go from step to step? So first, we have the API source, right? For Haskell, it'll be Stackage, for example. For Java, it is Maven Central. Yeah. For TypeScript, it would be, I don't know, whatever TypeScript uses, and I don't have to do that, so I don't. Then there's a sort of source extraction phase that happens, and we have a search database. Yeah? And this database is basically a collection of hypotheses for proof people. Yeah? So we have the search database, and this is all done pre-processed. So you can run this overnight, and it puts everything together. Yeah? Then the user comes, and he wants to give a query. So you have a query. Yeah? It's in some format, we'll come to that later. Yeah? And then the proof search takes the search database and the query, and it generates a set of proof trees. Yeah? And these proof trees are then ranked, yeah? And then you get the search results. Yeah? So let's do exactly the same thing again. Yeah? Let me just show you the little demo. So here we saw this demo with Hoogle. Yeah, and now let's do the same thing with type search. Yeah, so let's say let me reload this. Yeah, so this is this has the query already there, so I'm just going to type search typesearch.dev. There we are. Okay, now I'm a Java programmer and I want to do the same thing. I have a list of strings, yeah, and I want to filter all the telephone numbers out, and I would like some sort of function that does this filtering. Yeah? So what do I have? So in the language of Java, yeah, what we need is something like this. I need a stream of A's, yeah, and a function from A to booleans, and I want it to give me back a stream of A's back. Yeah, it's a sort of the type is sort of it's a specification of a type which is sort of these things are Java types, generic types and things like that, and the connectors are part of the framework that we use that makes it language agnostic. So I put this, I select Java there, and I get a list of all the functions of this type. So for example, I see, oh, there's drop while, but that's not what I want. I get filter, that's what I want, but I get other things also, right? So I have all this stuff, and I have a little piece of the documentation there, so I know what I'm doing and all that stuff. So that's good. Okay, so that's how it worked. That's a little demo of what that just happened. Okay, now how does this work? How does this work behind the scenes? Yeah. So one thing, so this is the search implementation, and you may be wondering, what is language specific in this whole thing? The only things that are language specific are the API sources and the source extraction. Everything else, you can use it for any language with these characteristics. So it doesn't need to have, but it supports subtype polymorphism, ad hoc polymorphism, and parametric polymorphism. So generics, overriding, and subtypes. So most of our general purpose languages have these three things. Yeah? Okay, good. How does this work in the beginning? So first thing is, what's this query language and what is the search database? What is the sort of the general language that we're trying to use? So the general language looks like this. I'm going to show you some examples. In Java, if you have a function like toString, yeah, which is member of this class integer, yeah. So in this case, if you put your sort of functional programming hat on, this is actually a function from integer to string. So it'll be translated to something like this. So you'll have integer hash. So this is just a separator of type integer hash to string is of type integer arrow string. Okay, good. Simple. What about a static member? A static member basically just doesn't have this the first parameter is basically the this in objects. Yeah? So that we don't have then. So we just have the integer that comes in as a parameter here, and the static means that I don't really care what the instance variable is. Okay, that's good. Okay, what about generics? Yeah? So over here I have the interface list of an arbitrary type, and I have a get method which takes the index and returns the element e, right? So how would this be translated? Well, it would be the name would be list hash get of type, and now we have for all e, since this is a generic function, for all e dot list e arrow int arrow e. So list e is the this variable, implicit parameter this, the int is the parameter that you pass to it, and this e is basically the return type. Yeah? So in our normal sort of functional programming understanding of types, this would be how it would be represented. And note, these things are just names, yeah, in the sense of Curry-Howard isomorphism. This would be the hypothesis that I can use to make my proof. In the case of TypeSearch, it would be the names of the functions that I would use. Yeah? And these things, this would be the type of the function. Yeah? Or if you put our proof goggles on, this would be the predicate that we're trying to prove. Yeah? For those of you who are aware of this Curry-Howard, who's aware of the Curry-Howard correspondence? Yeah, okay, cool. Then I don't have to go too much in this. Yeah, super. Okay, good. So yeah, so that's cool. Okay, now you're wondering how many proof rules do I need? Well, these are the proof rules that we needed. Yeah, so there are 5. Is it correct? 1? No, 6. Sorry, I lied to you. It's 6 proof rules, and surprisingly, this is all we need to capture this proof search. There's a little bit of cheating going on because there's one gigantic proof rule called resolution, which is the whole resolution. But yeah, it's simple enough. It's simple enough. So what do we have here? For example, hypothesis. It basically just says, oh well, I have this function already there, right? I can just use it. Yeah. If I just search for, let's say I'm searching for filter and I have filter in my thing, then I have it. Okay. This just says subset. Yeah. It says how I do subset. But this is identical to what's in PS's book, by the way. This is for all instantiation in the hypothesis. So if I have a generic function in my search database, I can instantiate it to a particular function and carry on with resolution. Yeah, this is basically implication elimination as proof, but if for example in the case of proof search, this would be, oh, if I want to find a function g of type g1 arrow g2, I can assume that I have this g1, I can say, oh, let's try to make this as something I have so that I get something later. So g applied to g1 and so on. So those of you who know Curry-Howard, this is basically that. Resolution is basically our workhorse for the proof, right? Proof search. And for all goal, if I have a for all in my goal, if I'm trying to find a generic function, then I just have to choose a fixed but arbitrary variable to do my proof later. Okay, good. So I'm going to show this with the same example that we did right now. This is the stream A arrow bool arrow stream A. I want to get the filter function out of this. Yeah. How does this work? First thing is that I have g for goal, right? I want to somehow find what this g is. At the end of the whole thing, I'll have to build up the whole proof tree, and at the end I'll have to unify this g with whatever's there in my leaves in order to get this. It's a classic like prologue style search basically. So I have this. I need to find some g of this type. First thing what I do, oh yeah, so correspondence. This A is basically from the stream of A, and these parts of the query are translated on these parts of the type. Yeah? Okay, first thing, since it's a for all syntax directed, I just have to free A. Yeah? If A is then fixed but arbitrary, therefore I replace it with some fresh new f. F is the fresh new variable. I have this, so now instead of g of this type, I have g applied to f, some new f. Yeah, is of this type. Now I have to search for this, right? I have something that's a bit simpler. Yeah, correspondences are there. Then I have these two, this implication. I can take that out. I can say, okay, I assume that I have something of type stream, so I can carry on with the search. So I have, so from here, I now have this G1 of type stream F, G2 of type F arrow bool, and so on. Here are the two correspondences. So from this sequence, I get to this sequence. This is now, instead of GF, it's GF applied to G1, which is of type stream F, sorry, and G2, which is of type F arrow bool. As you see, I'm sort of doing this, like building up this term. This is basically my proof term if I was doing proofs, right? But now it's my program, since I'm looking at it through the lens of a program. Okay, good. Now, somewhere in my hypothesis, yeah, I have the filter function, yeah, that I want to find. Yeah, somewhere I have this filter function, and so what will happen at some point in this proof search? This filter function will be instantiated, right? So how will that happen? It'll say, well, I have this f hanging around somewhere. It's a possible instantiation to this for all. So the resolution will basically do it, right? It'll stick it on. It'll say, okay, now I have another hypothesis. Filter applied to f. Yeah, this for all is basically a big lambda there in the type level. So it'll say filter of f is of type stream f, arrow predicate f, arrow stream f. So it'll just instantiate this t with an f, and so I have filter of f of this type. Okay, that's good. Now sort of everything is sort of come together, and now basically what will happen is that oh yeah, now I have a filter of f of this type, and now resolution will come in, and it'll say, oh okay, I have filter. Yeah, sorry. So now I have resolution. Resolution will basically do this function application on the hypothesis side. It will say, oh, I have now a term of type filter f, big F, G1, G2 of type stream f. Yeah, here are the correspondences. And now I have a little bit of a mismatch happening here. I have predicate f, yeah, on one side, and I have t arrow bool on the other side. So in Java, a predicate is isomorphic somehow to a function, to booleans, right? And so this is ad hoc polymorphism in a way. So what we say is that, hey, we have some types that we want to regard as isomorphic. Yeah? So we say that, for example, int and boxed int, I don't want to differentiate. So I say, hey, int and big int come to the same type. So we use something like a egraph data structure to handle that sort of thing. So we have some sort of isomorphic to make it into an isomorphic form. So that'll happen now, right? And yeah, and so at the end of the proof we'll have something, this sequence. We have, I want something of type stream f, yeah, and this is of type, this is the gf, g1, g2, yeah. G is something, remember, that's the variable I want to find out using unification, and I have this hypothesis. I have something of type stream f, filter f, g1, g2. So I'll say, I can use the hypothesis rule, and then I have to unify this term, and the only type variable and the only unification variable I have is this small g. Sorry, I should have put question mark small g so it's clear, but this is the only thing that I need to instantiate. So the instantiation would be g equals filter, and therefore g was initially the thing I wanted to search for, and therefore I find, one sec, there, this is my original thing, g is the goal, g is equal to filter, and therefore I have one possible case as filter. Good. Unification gives me g mapped to filter, and so filter is included in the search result. Are there any questions till now?
What if stream f and predicate f are given flipped by the user?
Good question. What if they are flipped?
Yeah.
It doesn't matter, because what will happen is that the order gets, it doesn't matter, because it'll be, in this case, the rule will basically, what will happen is that this stream f will go into the hypothesis in one step, the f arrow bool will go into the hypothesis in the second step, and therefore they'll all be in the hypothesis. And the hypothesis is set, it doesn't have any order. So that's cool, yeah. And also even in the hypothesis, the order doesn't make a difference, and even in the goal it doesn't make a difference.
It makes a difference for unification at the end, though.
At the end,
because you will have the arguments that you would have to do lambda filter,
Yeah.
lambda xy filter yx or something.
So you need a higher order unification?
No, we didn't use high order
There's a form
unification.
of pattern unification if you want to have it correctly.
Yeah, I'm wondering why does the order really make a difference? I'm trying.
In this presentation, it does. I'm pretty sure.
Yeah.
That doesn't mean that's what you implemented.
Yeah.
As long as we use the same unification variable G1, G2
Yeah.
on both sides.
I mean, the order would make. I'm trying to find this out. I think it. Let me think about this. We'll do this. Yeah. I have to think about this, but I don't think it does. But yeah, we'll see. Okay, cool. Any other questions? Yeah.
How do you handle stuff like vars, for example, that do not map cleanly to what you would have in Haskell?
Sorry, vars.
Variable arrays.
Var-
Var.
Oh no, that we don't do.
Okay.
Yeah. Would it be possible even? No. We would have to treat each and every function with the same arity in a separate way, just like what Prolog does. No, not possible. I'm wondering. What do you think? Yeah. Because then you would have to do the. Yeah.
I mean, I'm not sure there's a complete proof search, but there might be ways.
Yeah.
Just like you have var unifies with everything, so the saturation method is not bad, but then you have to be careful
Yeah.
not to. Like you have a lot of possible saturations that exist. You have to be a bit careful about that. And
Yeah.
if you are asking for a var array,
Yeah.
all var is just still listed by, then I know.
Yeah.
You can probably pretend it.
Yeah.
Something
I don't remember if we thought about this, if you want to support, but at the moment I don't have it in my head also. Yeah. Yeah.
You
Elliot?
said the predicate is isomorphic to like A to bool. Or
Yeah.
something.
Yeah. There it is. Mhm.
So I guess that has to be done manually for like a
Yeah.
few cases. Okay.
Yes, that has to be done manually. Yeah. It has to have some way of knowing this. Yeah. Also, the primitive types and the box types have to be done manually.
yes.
I see
Yeah.
it in Java.
By manually, you mean programmed into the extractor.
Yes. There'll be like a little prelude that says, "Hey, these types are the same."
Right.
Is a resolution rule related to resolution inference rule in classical logic?
Yes. So there is a reason why we use resolution. Yeah, because it's because I wanted to have as few proof rules as possible, and it somehow works. It's a nice way to do search in classical logic for this.
We
Yeah.
need we don't want classical proof, but we want intuitive proof.
Ah.
How do you prove your system
Ah.
intuitive?
This is intuitive. I don't. Is this? I do not explicitly do anything else than what's here from the proof rules. Does this have a problem? I have to think about this.
Maybe it's fine.
Yeah.
Maybe this form of formulation is fine.
Yes.
Maybe.
Yeah.
I'm not sure.
You
Yeah.
only have arrows.
I only have arrows.
So
Yeah.
Minimal logic. Resolution is complete for minimal logic.
Ah.
So I think Intuition's take or not doesn't matter here.
Yeah.
Maybe.
Yeah.
Okay. That makes sense.
Yeah. Because I don't have this. I think the problem would be if I had a knot on the other side, but I don't have a knot in this. So there's no knot. So yeah. Ah, but cool. This is something I didn't think of, but yeah, it just worked. Cool. Any other questions? Yeah.
So, I think sometimes the set of hypotheses can be arbitrarily large.
Mm.
For example, suppose you have the successor function
Yeah.
in the hypothesis.
Yeah.
Then you can apply the successor function to integers.
Yeah.
How can we avoid that?
That's a really cool question, and this was actually the problem that we had. You know, in typical proof search, right? You're happy if you get one proof. Yeah. In this sort of proof search, you end up getting infinite amounts of proofs, even if you go down one branch. And that was something that it's clear now, but we were thinking, hey, this allows us. This basically means that the proof methods that we use currently are not applicable to this sort of search. Those proof methods are dealt at finding one proof, because it's sparse. The space of proofs is super sparse, and here the space of proofs is super dense, right? And you want the one that you want. Yeah, that's the problem. And here, that's sort of a bit of further work. So we have some heuristics on how to traverse the tree. We do more of a breadth first search than a depth first search, and we try to say that, hey, if I want to use as many hypotheses as possible, that's one thing. I want to first instantiate all the hypotheses and then do so. And the other thing I do here is that I try to get proofs with just one term, so not these program syntheses types of proofs. So that narrows down the space a lot also. But yeah, you're right, it gets too much. And a nice way to do this would be to do this in a lazy manner, to have a data structure where you just sort of keep on pulling and it just gives you the next best one. Currently, this has to be done properly. Yeah.
I see. Thank you very much.
Thank you. Any other questions? Okay. Cool. Yeah. So we've seen this in action. It works. Feel free to try it out. This is a prototype. It's got the whole Java standard library inside. You can use it. Someone said they would be interested in doing it for Go. That's sort of working. There's someone in their hobby time wanted to do it. You can sort of rate it, give us some feedback on. You said, maybe this should be on top, so Mark can collect these things. Yeah, and we hope to have something like this that's sort of language agnostic. So, for example, typically people do front end and back end in different languages, and so they may want to know the same function in two languages. So it would be nice to sort of have this. But yeah. So further work, make use of pre-existing proof search algorithms. Right now, we've just made something, a search algorithm. How we think it should work, because the existing ones just give us too many proofs. Improving some ranking, possibly a lazy algorithm, and to really try this code synthesis in a serious way. Currently, we just got like successor, then successor. That doesn't really do anything, right? So to have that needs some work. Yeah, add support for additional languages, and so there were some things that surprised us, right? And so we saw that actually in this setting, this idea of this problem with subtyping doesn't really come here. I mean, it's non-existent. My worries were not well founded. Yeah. So type-directed API search is possible, yeah, for mainstream languages. It's just the question that no one does it. And this can be done in a systematic and language-independent way, not something ad hoc. You can use really well-founded principles from algebra and from type theory to do something like this, and something super practical from something super elegant. Yeah, that's it. Yeah, so elegant solutions matter. Cool, thank you very much. How am I doing for time?
Fine.
Cool. 29:59. I just hit it. Nice. Perfect.
I have a question.
Yeah.
How fast is it compared to Hoogle's? Because the proof search that you demonstrate, that looks slow. So
let's do it. Yeah, let's do it. This is running, by the way, on Mark's computer in his basement in Switzerland. just so that we.
Faster than Netherlands.
Yes. I mean, once I had a demo and I said, hey, Mark, it's not working. He said, oh, sorry, I had to plug it out because I had to put my vacuum cleaner on. So yeah, I told him to please keep it on. Please do your cleaning at another time. But yeah, we can try some. I mean, I don't know, string to file. It's actually working. That's how fast it was. Random int.
And can you show using subtyping in the query?
Yeah, sure. What would you like me to search for? This was subtyping in the query. Let's do object. What is an object? Something hash. What does hash give out? Hash gives so toString. toString is subtyped. String to string. String to string. Let's try this. System flavor map. What? System flavor map. I'm looking for Java lang string, public string. Okay, what about toString?
Do you need this as an argument?
No. It just treats it like any other argument. I should have toString. Control C. Control. To. There it is. toString. This is an object, and it found it. So yeah, and it's reasonably fast. I mean, there's no real caching happening.
And so, if you had a language like Haskell that has type classes,
Yeah.
you would model that with subtyping, or
I think the
No.
right thing to do about type classes is ignore them.
Yeah.
you don't use type classes in your Hoogle queries?
It's not. You don't really.
Yeah.
Or
Google
just
doesn't do a very good job.
No.
Yeah.
just dictionaries,
Yeah.
dictionary arguments.
Yeah. I'm not sure. I don't think we can just use the normal subtyping stuff there. It's something quite orthogonal to this.
There is a typing and stuff.
Yeah.
And how about higher ranked polymorphism?
Higher order polymorphism.
Yeah.
No.
Like
Won't
functions,
work.
or you mean
The
ST
formal,
model?
Yeah.
like ST models.
Yeah, no, it won't work because the proof rules don't have it, right? So, no, it would work because I would have I do have it. Yeah, it would work. It would work. It's just that mainstream languages don't have that.
Exactly.
So when Java gets that, we'll be ready.
So, but not
When
but,
Rust gets it.
but not for functor like higher ranked polymorphism.
Like for example,
Well, so it's not quantified over type, but type to type.
ah,
Higher kind
Ah.
of, yeah.
higher kinded polymorphism. Then I would have a type. How would I even represent this?
So type remarcation is needed, I think.
Yeah,
That's literature.
yeah, okay,
Confusion from Germans.
yeah,
But mainstream languages doesn't have it. So
Yeah.
It doesn't matter.
yeah,
I don't think it's particularly harder
yeah.
with the rules that you have. It's just very finicky.
Yeah, I'm unsure how I would. Yeah, so the sort of target language were Java, TypeScript. You know. So I was but these things are interesting. I mean, if Haskell needed another Hoogle, maybe we could think about these things. But Hoogle, by the way, Hoogle is not our work, right? It's from Neil Mitchell. Great stuff. And we got in touch with him before we did this. And Hoogle had a number of revisions, right? So in the beginning, he used something like this, and then now it's like a mix of different things. And so just for information. And unfortunately, there's no real documentation. He did this in his free time, right? And so, but yeah, that's great work. Yeah.
What does the database actually do? How long does it take to crunch through Maven?
I have to ask Mark, but I think it took, didn't take long. I think over a night or something like that. Or even
And what does it do?
it has like an index. It has like a database. It stores it in memory or on the disk. And every time a query comes, it uses the database to populate the hypotheses. So I guess
But does it process it in any way to make the query faster, or it's
No.
just the types of all of
just the types. No, there's no optimization being done right now.
I see.
It's all very. This is a master's thesis.
Yeah.
So it was a proof of concept.
For the
So
PhD.
you produce
Yeah.
hypotheses based on the queries. So it's a kind of premise selection in certain improving.
No, it's all the hypotheses, just
All of it?
dumped in. All of it.
What kind of data structure are you using for your database? Is just
Oh, I have to ask Mark. He he took care of that. But yeah, I was impressed that it even worked. Yeah.
And, what happens if you give unprovable goal? Like
Yeah.
exclusivity needle or elimination of duplication?
That's true. Let's try it out. I hope the camera is not working.
Also, I'm wondering what if you give Go that requires general recursion like a
Yeah.
fixed point operator.
Oh wow, that's cool. Someone give me a goal. Let's see what happens. It will also be interesting to see that no function like this exists in Java. So that's what type of what doesn't work?
Like fix.
Fix, yeah.
Fix.
Okay. Can someone
Version of fix.
who has
For
the
all A to A to A. A to A
mhm.
to A.
To A.
Okay.
Right, I don't know, can you have for, yeah, you can have for alls when you're
Yeah.
doing queries.
A. I can't have no. I can't put no. I can only I can't put for all inside my query. So A to A. So my top level language doesn't allow it. I could have allowed it, but we didn't. No, I can't do this. No, I of course it'll give me some. Let's try it, but I can't put the for all in there. So let's do it anyway.
You might find something that's
Bad request. Reason mismatch output.
Expects a name.
Can't do everything with Java.
Yeah. Is that the problem? I think-
Can you actually have a like a pointing bracket say on its own without a name in front of it?
Yeah, that we can. Let's see.
Maybe it's the nested arrow and
Oh. Oh, there are actually some.
The next one should just be A, not A inside. Where is this?
Okay.
I can't read Java.
So would for all AA give you all of the constants? I mean,
All of the identity functions, yeah. So I could do for all A. I think here it's just giving some indicator values to for something that has a side effect.
what is it?
So there's a write
That doesn't
also.
read like Java.
Write gives back an A.
A void?
A void. I don't know what this is. Yeah.
For all A, returns void.
So A arrow A we can try.
And these are void functions, actual void functions.
nice.
I think it's just just a printer that goes crazy.
Let's try that. Read is also good. Yeah. I think we're entering some sort of no man's land type type theory no man's land.
What fresh A's?
When you write A like this,
Yeah.
it is existentially qualified. That's a unification
That's
variable.
yeah. No, that's this will be all the for alls come in the front, just like in Haskell. So when you don't
In the
so
query, yeah.
in the query for all A dot A arrow A.
So that's what this type means.
Yeah.
And that is not what it finds.
Yeah.
Maybe it is.
So
You
the thing
read
is
all A and get an A. That's not what. No, you read
It's-
void, right?
So it does some sort of approximation also. So right now, so the thing is that if you know the exact type, right, it's likely that this is not the function you really want. It may be sometimes you know somewhat what you need, but it may be that the function that you need has more arguments. And you want those as well. So it's trying to approximate that a bit here as well. So it's saying, oh, well, arrow A is contained in this. So it's trying to, the actual query it generates is something like this. It'll generate something like for all A dot existential B arrow A. So it's trying to say that, hey, if I don't find anything that matches exactly this, just give me something that seems to match also.
But do we agree that it believes that there's a coercion from void to any A? Which I think is a slightly heroic assumption.
This is basically how it should be in the Java doc. Let's see the Java doc.
Is it?
Let's see the Java doc.
Yeah, I'm going to learn some Java today.
Who knows Java?
Condolences.
Shit. Hey, we've This is an achievement already.
Wait, it's just a for.
Here there's something param type of okay returns.
I don't think you get a medal for finding unsoundness in Java.
No. It's well documented.
Yeah.
Okay, let's see. Signature of read java.base.
Very searchable.
Java doc read java.base. Oh no.
Cannot find via Google. Someone should make a search tool so we can find it.
Oh, there's people know Japanese, so I guess. Oh, this is the channel.
At the asynchronous channel or whatever the package was, maybe.
Okay, so what should I do?
You can copy the whole declaration. Java and IO.
Got it.
But you just have to forward the beginning of the line, and then the return type, and then the rest of the point you had at the beginning of the
There you go.
No, I think you just assume that you encode his voice into A. No?
No, it's just how you write forwards in Java.
Oh. So then it's not A to A.
No, it's not A to A, but if you
Not
want
even
to
at all.
Future.
It's the second.
A void.
It's A.
Yeah.
Yeah.
That's just the for all.
Yeah, it's the for all applied to the function, but then it's not A to A, is it? Maybe you do more approximations than you.
Yeah.
On.
Yes. Yeah.
To what if something.
Yeah. There is more approximation to that then.
Right,
Yeah.
yeah.
Yeah. Okay. I mean, the good thing about type search is that if you find a proof, it doesn't have to be correct, right? It's just a hint. So I guess there are many more approximations that happen here.
How do you rank the results?
How do I like the results?
Rank.
Rate. So currently we have a few heuristics as to how we do the search in the tree. So it's more breadth first search, and we say that, we want to first exhaust all our hypotheses. So we first generate those proof trees, and then we do everything else. After that we say, okay, now instantiate the existential variables that we also put in and all that. So it's quite ad hoc at the moment. Yeah.
If the tail is an existential variable, isn't that this is correct then, isn't it? Because the tail can just be byte buffer to blah.
Isn't the first argument?
Okay. Yeah.
I think that the
prop.
problem.
So even if you look at it like binding to the right
Yeah.
and returning anything else, it's still not correct.
Yeah.
Or it's still a void returning function. So.
Yeah. So this is the first time that such detailed critique has been at the type theory level has been
These people don't actually want to find a Java method. Great, thanks.
Yeah, thank you very much. Thanks, you too.